Good morning. Today we discuss a new chapter, Newton's laws. This lecture is based on our textbook, Mechanics by Klapnab. In this chapter, we have to discuss about Newton's three laws and some of examples based on Newton's laws. And some other forces in the universe, and we dealing with specific forces and the concept of center of mass. Lastly, we discuss the conservation of momentum. So we starting with Newton's laws. Up to your plus two classes, when we dealing with some laws and theories, you will get some statement of the law or the theory, and then some explanation and example or applications of the particular theory or the principle. But now we dealing the Newton's laws from a different angle. So before going too deep into the laws, I just mentioned the three laws. We know that the first law, it states that every object will remain at rest or in uniform motion in a straight line unless compelled to change its state by the action of an external force. That is, until an external force applied to a system or a object, it will remains its own state. It may be in rest or in uniform motion in a straight line. And the second law. Second law explains how the velocity of an object changes when it is subjected to an external force. We are familiar with the Newton's second law by the statement that the applied force is directly proportional to the rate of change of momentum. Or we can define the second law as the force is equal to the change in momentum per change in time. And the third law, it states that for every action, there is an equal and opposite reaction. Or if a object A, if a object capital A exert a force on object capital B, then the object B also exert an equal force on the object A. Now we go to the topic from our textbook. We know that the Newton's laws are the basics of mechanics. So the fundamental laws must have the experimental support. So we have to get a clear idea about which part of Newton's laws are based on experiment and which part are matter of definition. To achieve it, we must analyze all the laws of Newton's individually. We start by appealing directly to the experiment. Unfortunately, experiments in mechanics hardest in physics because of motion in our everyday surrounding is complicated by the forces of gravity and friction. Have you know? Newton's first law states that every body continues its state of rest or uniform motion along a straight line unless it compelled by an unbalanced external force. Just consider any situation in our everyday life. If we move a toy car a little bit, after some time, it stops. Initially, it is moving. After moving some distance, it stops. From this situation, we cannot attain the law of first, first law of Newton. Newton's law states that it will go on moving. We know that the toy car gets stopped by due to the force of gravity and by the frictional force. So, you do some experiment to, to verify some laws in physics. It is very hard to conduct because here everywhere there is gravitational force and there may be some slight frictions. So we have to eliminate all such disturbances and examine very simple systems. If we eliminate the gravity and friction, we can analyze is the first law is experimentally valid. So, in our Earth, it is impossible to eliminate the gravity. So, what will be our next option? What will be our next option to eliminate these type of disturbances? Can you guess? Just think of space. We know that in space, there is no gravity and there is no friction. So, a one way to eliminate these disturbances, we have to enroll as astronauts. It is very difficult because we know that it must have very financial burdens for doing such experiments. So we think of another way to eliminate these disturbances. Such a thing is done in laboratory. The second way is a device known as linear air track. But it is only in one dimension. Can we go to the details about that? It is the figure of a linear air track. Just look at the figure. Can we see? Here, a triangular, hollow, metallic pipe which has an inlet for giving compressed air, and here On the two sides of the triangular shape, there is some small holes or air jets. The compressed air given to the hollow pipe will stream out through the small air jets, and it is called as a rider. It can fit into this triangular shape very well. And there is some leveling screws. Okay, so the linear air track is a hollow triangular beam. It may be 2 meter long or more than that, and it has many small holes which emit gentle streams of air. And a rider. Did you see in the figure? The rider rests on the beam, and when the air is turned on, the rider floats on a thin cushion of air. Because of the air suspension, the rider moves with negligible frictions. If the track is leveled carefully and if we eliminate any stray air currents, the rider behaves as if it were isolated in its motion along the track. That is, we know that the rider has some mass. Okay, it will act downward. Due to the airflow upward through the small holes, that force will cancel with the weight of the rider, and so the rider just float over the track. So the rider can move through the track without any friction, as It does not touch to the track. It just floats over the track. The rider moves along the track free of gravity, friction, or any other detectable influences. Just watch some portion of this video. This is a linear air track, and the rider moves on the linear air track. It is the leveling screw, and it is the pipe from compressor, and there is a pulley. It is used for some experiments, and it is another linear air track. It is length more than 4 meter, and here also we can see a compression pump, and it is connected to linear air track, and in the air track there is some small holes, and it is two riders, and there is some provision to put some mass on rider. Now let us observe how the rider behaves. We know that the linear air track, it is a device using that we can do experiments as there is no gravity and no friction. So suppose we place a rider on the track and carefully release it from rest. That is, the rider is at rest, it is placed on the track. According to Newton's first law, it will continue its state of rest. We can see that as we expect, the rider stays at rest, at least until a draft hit or somebody bumps the apparatus. Okay, then if we push or pull the rider very slowly, what happens? We know that there is no gravity, there is no friction, then the rider will move through the rider freely without any change in its speed. The rider continues to move along slowly and evenly, neither gaining nor losing speed. This is contrary to our everyday experience that moving bodies stop moving unless we push them. The reason is what? The friction. The friction usually plays an unsatisfactory role in our everyday life. But we know that friction is, in some cases, helping us also, isn't it? Okay. So we can observe the motion of the rider on the track in the video. Here, he turning on the air compressor and check the levelness, and when he put the rider, it stay there and just kick. It moves slowly and it then return back. Now it is moving very fast. At the end, there is a spring mechanism to return back it. Now it is quite fast. Now it is very slow. It is very fantastic because when we moving any object very slow, it will come to rest very soon. But here it does not come to rest. Okay, So, using this one-dimensional linear air track, we can experimentally prove the law, Newton's first law. Here, we only check the validity of the first law. So, it is only in one dimension. In the similar way, we can also construct a two-dimensional air turbine analogous to the one-dimensional air track. Just consider a smooth sheet of glass with a flat piece of dry ice. Okay, then when an object is placed on above the dry ice, it will move in two dimension without any friction. Okay, because of the evaporating dry ice provides the gas cushion. So we can find that any rider moves with uniform velocity. But the three-dimensional isolated motion is hard to observe. But let us for the moment assume that our experience in one and two dimension also hold in three dimension. We therefore surmise that any an object moves uniformly in space provided there are no external influences. So we discuss the validity of Newton's first law. We know that the motion is relative, isn't it? That is, the motion has meaning only with respect to a particular coordinate system or with respect to any particular frame of reference. For example, in describing motion along the linear air track, we implicitly used a coordinate system fixed to the track, isn't it? Have you the idea about frame of reference? Okay, just look at an example. Okay. Consider three persons. Let they are A, B, and C. Okay. Consider this is B, a train. That is moving on a track, and here it is the platform. Is the platform. Train is moving this direction, and A is sitting here, and B is sitting here, and the person C is standing here. Okay. Then when A or B looking towards C, they feel that C is moving backward. If the train is moving with a velocity v, A feels that the C moving backward with a velocity v. It is applicable to B also. That is, if B looking at C, he also feel the same. That is, C is moving backward with a velocity v. Actually, A and B both are sitting in the train, and C is standing in the platform. I write here A sitting, that means not moving, sitting on the train. B also sitting on the train, and C is standing on the platform. A train is moving to the right with a velocity v. Then, according to C, when the person C look at A and B, he feels that A and B moving with a velocity v. Both A and B moving with a velocity v. Okay. Then what about A and B looking each other? What they feel? Both are sitting in the train. So they feel that they are at rest. So the state of A, B, or C with respect to some persons, that is the state of B with respect to C and with respect to A are different. With respect to A, B is at rest, and with respect to C, B is moving. Actually, B is at rest with respect to the train. Okay, so we can say that the motion is relative. So here we use the term with respect to A, with respect to B. So we fix some reference with reference to C, B is moving and A is moving, or that reference taken as a frame. Okay, that is frame of reference. In our example, in describing the motion of the rider along the air track, if we choose a frame or a coordinate system that fixed on the track, we can say that when we fixing a coordinate system on the track, then the rider moves with a constant velocity. Such a coordinate system is called as inertial system. Not all coordinate systems are inertial. In such coordinate systems, that is, in a non-inertial coordinate system, the rider does not have constant velocity. Okay. So in inertial system, in our case of experiment, it must have constant velocity. If we viewing the same from some accelerating coordinate system, the rider moves without constant velocity. So we can say that an accelerating coordinate system is not inertial. We can classify the systems as inertial system and non-inertial system. Inertial frame of reference or non-inertial frame of reference. In inertial frame of reference, no, from our rider experiment, rider experiment, we consider only that case here. Our rider experiment, the rider with will be moving with a constant velocity when we observing it from initial frame of reference. However, it is always possible to find a coordinate system with respect to which isolated bodies move uniformly. This is the essence of Newton's first law of motion. So we can say that Newton's first law partially experimental and partially